Now let's see the plane parallel approximation. Since the length of the atmosphere of a star is small compared to the radius of the star, we can assume that r, the radius, is much bigger than 1, and ignore the second term in the equation of radiative transfer in spherical coordinates. So the equation simply becomes, now this is equivalent to ignoring the curvature of the star, which names this trick than the plane parallel approximation. Now notice that we can also absorb the cosine in the optical depth. And if we write then that tau is tau over cosine, then the equation would have the same form as we have studied so far. This is actually a geometrical construct, which is illustrated here in this figure. You have here the thin plane parallel layer, where we are ignoring the curvature. Now the optical depth is defined along the ray, and for a plane parallel atmosphere of depth dx, these rays here, the rays are coming perpendicular to it, will have a path dx. But rays are going obliquely to it are going to have to traverse a length that is dx over the cosine of the angle. We're going to introduce also an important mathematical change. That is, we're going to define the direction where the optical depth increases. In this case here, you have a star in the outside, or a source in the outside, and then the photons are propagating inwards. But let's assume a situation in a star where the photons are traveling upwards from the center to the atmosphere. But we are measuring optical depth in terms of material in our line of sight. From our perspective, we are outside the star. The optical depth in the atmosphere is increasing with depth opposite to the movement of the photons. So the photons are moving upwards, but from our perspective, the optical depth is increasing inwards, opposite to the movement of the photons. So if optical depth and geometrical depth increase in opposite directions, the infinitesimals must have opposite sign. So we're going to redefine the optical depth in terms of the negative of the geometrical depth. The photon flow is upwards, but the optical depth increases downwards from our perspective. So if you align the z-axis as going upwards, that means that the optical depth is increasing with the negative of the coordinate. Going to greater optical depths, we're encountering exponentially more intensity. So the sign reversal simply means this change of perspective. So the form of the equation of radiative transfer usually used in the plane parallel approximation is this form with the signs reversed. So if kappa rho z, or kappa rho r now, in the plane parallel approximation becomes negative at d tau, that means that the sign is in the right-hand side, they're going to flip. You then have that cosine theta di dt is equal to I minus s. The sign reversal now is because the intensity increases with negative geometrical depth.